Have you ever stopped to think about how strange it is that everything in the universe seems to line up just right for us to exist? Gravity has the perfect strength to hold stars together without crushing them. The sun gives off just the right amount of heat to keep Earth alive instead of frozen or burning. Even the tiniest details of physics, like the strength of the forces that bind atoms, seem almost too perfect. Change any of them by just a fraction, and life as we know it wouldn't even be possible. So the big question is why? Is it pure luck, some hidden necessity in the laws of nature? Or is there something deeper at play? The fragile balance of the universe. When scientists describe the universe as finely tuned, they don't mean it casually. They mean that the values built into nature, the strength of gravity, the mass of the proton, the balance of nuclear forces, the rate of cosmic expansion are not just numbers, they are the settings on which everything depends. Adjust them by the tiniest amount, and the story of the cosmos changes so completely that life as we know it could never appear. It's this delicate balance, this narrow window of possibility, that makes the question of fine-tuning so powerful. Take gravity. It feels like the most ordinary force. We drop a stone and it falls. We stand on the ground and feel its pull, but on the cosmic stage, gravity is the sculptor of everything. If it were a little stronger, stars would collapse under their own weight, burning through their fuel in a cosmic blink, exploding before they could ever nurture planets. A universe like that would be full of brief flashes of light, and then silence. If gravity were weaker, the opposite would happen. Matter would spread too thinly to ever ignite fusion. No stars, no heat, no chemistry, just endless cold and darkness. Our universe sits right in between, where stars live long enough to forge elements, and planets can orbit stably for billions of years. Then there's electromagnetism, the force that binds electrons to nuclei. If it were much stronger, electrons would cling so tightly that chemistry as we know it would be impossible. Atoms wouldn't combine into the rich structures needed for biology. If it were weaker, atoms wouldn't hold together at all. The complexity of molecules, proteins, DNA, and cells depends on this precise strength. Even the colors of light we see, the way photosynthesis works, the sparks that drive our own nervous systems all flow from the fine balance of this force. The nuclear forces deepen the mystery further. The strong nuclear force is what holds protons and neutrons together inside atomic nuclei. Too strong, and stars would lock up their fuel almost instantly, producing little variety in elements. Too weak, a nuclear wouldn't bind at all. Hydrogen would exist, but nothing more. The weak nuclear force, despite its name, is just as crucial. It governs the delicate reactions that let stars shine steadily instead of erupting chaotically. It also drives radioactive decay, which warms the interiors of planets. Without it, Earth's geology might be lifeless stone, never recycling elements through volcanoes and tectonic activity. And then there's the cosmological constant, a small but critical value that controls the rate at which the universe expands. If it were even slightly larger, matter would never have clumped into galaxies. If it were smaller, the universe might have collapsed before stars ever formed. As Steven Weinberg pointed out decades ago, the fact that this constant has the value it does is astonishing. It allows a universe vast and old enough for stars, planets, and eventually living beings to appear. It isn't just that each of these forces has to be balanced. What's truly staggering is that they must all work together. They interact in ways that are tightly interwoven. Change one, and the rest unravel. A stronger gravity might be balanced by different nuclear forces, but not in a way that allows stable chemistry. A slightly different cosmological constant might be survivable only if gravity or electromagnetism also changed. But that combination doesn't exist in the equations of physics we know. The parameters seem locked together in a narrow corridor where everything lines up just right. Physicists sometimes describe this as a Goldilocks universe: not too hot, not too cold, not too fast, not too slow. But this isn't just poetic language. The margins are vanishingly slim. Paul Davies once said that the impression of design is overwhelming. because the odds of landing in this narrow, life-permitting band seem so small. Even if you prefer to think of it as chance, it is chance on a scale so extreme that it tests our imagination. To make this clearer, imagine a mixing board with dozens of sliders, each one controlling a fundamental property of nature. Slide any one of them up or down, even slightly, and the universe produces nothing but chaos, sterile particles, or short-lived flashes of energy. Yet, here we are, in a reality where every slider sits in the narrow zone that allows stars to shine, planets to form, and chemistry to flourish. It's like finding a safe combination by spinning a lock at random and landing on the exact sequence needed. And this isn't just abstract theory. Observations back it up. Without the exact balance of nuclear forces, carbon would never form in stars. Fred Hoyle, who predicted a crucial resonance level in the carbon nucleus, once remarked that the universe seemed put together by a mathematician because the numbers lined up so precisely to allow carbon, and by extension life. Later experiments confirmed his prediction. Hoyle himself, though an atheist, admitted that the fine-tuning of nuclear physics left him shaken. The fragile balance of the universe isn't fragile in the sense of being weak. The laws of physics are unyielding, but they are fragile in the sense that almost any alternative arrangement would leave nothing to talk about. No planets, no oceans, no minds. Our existence depends on a cosmic knife edge. And the fact that it held steady long enough for us to emerge is one of the deepest mysteries we face. This is why fine-tuning unsettles so many scientists and philosophers. It doesn't just tell us that the universe works. It tells us that it works in a way that seems improbably precise, as though reality had to hit a very small target in order for us to be here. Whether that precision is the product of chance, necessity, or something beyond either, the fragile balance remains the same. Every star in the night sky, every breath you take, every thought in your mind, all of it rests on numbers that could have been different but aren't. Time and fine-tuning. When people talk about fine-tuning, most of the attention goes to the numbers, the forces of nature, the constants, the delicate strengths of gravity or electromagnetism. But there's another layer to this puzzle that is just as important, and in some ways even more mysterious: time. The universe didn't just need the right physical laws, it needed them to play out on the right schedule. It isn't only about where the sliders of physics are set, but also about when things happen. How fast or how slowly events unfold. The timeline of the cosmos is itself a kind of fine-tuning. Think back to the beginning. In the first fraction of a second after the Big Bang, the universe expanded faster than anything we can imagine. That expansion had to be controlled with extreme precision. If it had been just a little faster, matter would have thinned out too quickly for stars and galaxies to ever form. The universe would have been a diffuse fog of particles expanding forever into emptiness. If it had been slower, gravity would have pulled everything back together almost immediately, ending in collapse before the first star could shine. The expansion rate sits right in the narrow corridor that allows matter to clump into stars, galaxies, and eventually planets. That is a timing issue as much as a force issue. But timing continues to matter long after those first moments. The earliest stars that formed were huge, unstable, and short-lived. They burned bright and died young, exploding as supernovae after only a few million years. These stars were too fast, too violent to allow life anywhere near them. Yet their explosions seeded the universe with heavier elements, carbon, oxygen, iron, that later generations of stars and planets would need. The universe had to wait. Only after billions of years, after multiple cycles of stellar birth and death, did enough of the right elements accumulate for biology to become possible. If life had tried to start earlier, the universe would have been sterile, filled with hydrogen and helium, but little else. This patience is built into cosmic history. Earth formed about 4.5 billion years ago, but it wasn't ready for us then. The planet had to cool, the atmosphere had to stabilize, and the oceans had to form. Life may have begun relatively quickly, but it took billions of years more for complexity to evolve. Multicellular organisms are a recent development in cosmic terms, and intelligent life is even younger. We arrived at the tail end of an unimaginably long process, timed with remarkable precision. Even our star, the Sun, is on a clock that matters. It is middle-aged, stable and steady. Smaller stars flare unpredictably and could sterilize nearby worlds. Larger stars live fast and die young. The Sun sits in a sweet spot, giving Earth billions of years of stable warmth. If intelligence had arisen too early in the universe's timeline, before enough stable stars had formed, there might never have been the chance for long-term evolution. If it arises too late, stars will be dying, galaxies will be dimming, and the conditions for life will be vanishing. We are here during a rare window where the universe is active, rich with energy, and supportive of complexity. Cosmologists sometimes call this the cosmic coincidence problem, a term coined by leading cosmologist Paul J. Steinhardt. Why do we live now, in this particular era, when conditions are just right? There was a time when the universe was too young, and there will be a time when it is too old. In the far future, stars will burn out, galaxies will drift apart, and the universe will become a dark, cold place where life can no longer thrive. We live in the brief middle act where everything aligns: the expansion rate, the age of the stars, the balance of elements, the stability of our own sun, a fleeting moment of harmony, allowing life and consciousness to awaken just long enough to witness its own story unfold before the curtain of eternity falls once more. John Barrow and Frank Tipler, in their work on cosmology, pointed out that fine-tuning isn't just about constants, it's about chronology. For life to exist, not only must the laws allow chemistry, but the universe must be old enough to have forged the materials life requires, and not so old that those conditions have already slipped away. It's a moving window, and we happen to be inside it. This gives fine-tuning a different flavor. It isn't just a matter of forces being right, it's about them being right at the right time. The universe has unfolded like a long-chain reaction, each stage preparing the way for the next. Expansion made galaxies possible. Galaxies made stars. Stars made elements. Elements made planets. Planets made chemistry. And chemistry, given enough time, made life. At every stage, timing mattered. Change the tempo, speed things up or slow them down, and the sequence breaks. It's sobering to realize how temporary this balance is. The perfection we see now, stars blazing, planets orbiting, galaxies full of energy, will not last. In 1 trillion years, even the brightest galaxies will fade into darkness. The fragile balance of time that makes life possible is not eternal. We live in a rare, fleeting moment when the universe is still fertile. That makes our existence not just improbable, but profoundly tied to timing. In the end, the fine-tuning puzzle is not only about numbers written into nature, but about history itself. We are here because the universe expanded neither too fast nor too slow, because stars lived and died before us, because our sun is stable in this epoch, and because we emerged in the one sliver of cosmic time where observers are possible. The universe is not just balanced in space, it is balanced in time, and we are living in its brief, perfect interval: stars, planets, and habitability. When we think about what makes the universe suitable for life, stars are at the center of the story. Without them, the cosmos would be nothing more than endless dark clouds of gas, too cold and too empty for anything interesting to happen. Stars are not just points of light, they are factories where the raw materials of life are made. In their cores, under crushing pressure and unimaginable heat, lighter elements like hydrogen and helium fuse into heavier ones. Over billions of years, this slow but steady process produces carbon, oxygen, nitrogen, iron, and everything else that makes up planets, oceans, and living creatures. When stars eventually reach the end of their lives, they scatter these elements into space, seeding the next generation of stars and planets. It's a cycle, and our existence depends on being late arrivals in that process. Now think about how rare the timing has to be. The first stars that ever formed in the universe were massive and burned out quickly, exploding into supernovae before life could have had any chance to appear. Only after multiple generations of stars lived and died did the universe have enough of the right ingredients to support life. We were born into a cosmos that had already been enriched by billions of years of stellar activity, Had we appeared earlier, the universe would have been a sterile place, rich in hydrogen, but poor in everything else. Life requires. It isn't only the stars themselves that matter, but the kind of star a planet orbits. Our sun is a good example of stability. It's not too large, which means it burns its fuel slowly and steadily instead of in violent bursts. It's not too small either, because smaller stars, red dwarfs, tend to flare unpredictably, blasting nearby planets with harmful radiation. Earth orbits a star that has been giving off just the right amount of light and warmth for billions of years, and it hasn't changed drastically enough to destabilize our climate. A tiny variation in stellar behavior could have meant a frozen wasteland or a scorched desert, instead of a planet with oceans, forests, and breathable air. The position of Earth in relation to the Sun is another piece of this delicate puzzle. Astronomers call it the habitable zone, the narrow band of space around a star where conditions are suitable for liquid water. Too close and the water boils away, too far and it freezes. Earth sits almost perfectly in that zone. It isn't just about distance either. The planet's atmosphere plays a role in keeping temperatures stable. Our blanket of air traps just enough heat to maintain a climate that supports life. Without this balance, Earth could have ended up more like Mars, which lost much of its atmosphere, or Venus, which kept too much of the wrong gases and turned into a greenhouse inferno. Even our moon has a part in this story. Without it, Earth would wobble chaotically on its axis, leading to wild climate swings that might have made it harder for complex life to evolve. The moon helps stabilize Earth's tilt, giving us relatively steady seasons. That may not sound dramatic, but when you add up billions of years of evolution, that stability is priceless. It allowed ecosystems to develop without being constantly wiped out by climate extremes. Our oceans, guided by the moon's gravitational pull, also experience tides that help circulate nutrients and may have been crucial for the first steps of life in shallow coastal waters. Then there's Earth's magnetic field, another detail we often overlook, generated by the movement of molten iron in the planet's core. It shields us from solar radiation and cosmic rays. Without it, our atmosphere could have been stripped away, leaving us as exposed as Mars. Life needs protection as much as it needs water and warmth, and our planet happens to have the right kind of defense system. When you step back and look at all these layers, stellar stability, planetary distance, atmospheric balance, the role of the moon, and the shield of the magnetic field, it becomes clear that habitability isn't about one lucky factor. It's a combination of many, each one necessary. If even one of these were missing or altered, Earth might not have been able to support life at all. That's why astronomers searching for planets around other stars aren't just looking for worlds the right size or at the right distance. They're trying to piece together the same delicate combination of factors that we see here, knowing how rare it must be. The more we study it, the more it feels like Earth is a cosmic exception rather than the rule. And yet, we exist. Somehow, everything aligned in a way that let this planet become a home. Whether this is an incredible stroke of chance or part of a deeper pattern in nature is still an open question. But what's clear is that habitability depends on far more than just being in the right place at the right time. It's about a web of interlocking conditions that all had to fall into place. The anthropic principle. When scientists look at the universe and notice how every detail seems perfectly aligned for life, it raises one of the strangest questions in physics. Are these conditions genuinely rare, or do they only feel that way because we are the ones asking? This is the essence of what's known as the anthropic principle. On the surface it seems simple, but once you unpack it, it changes how you think about almost everything in cosmology. The phrase itself was introduced by the British physicist Brandon Carter in 1973. He realized that when we study the universe, we are never neutral observers. Our very existence places restrictions on the kinds of universes we can find ourselves in. Imagine for a moment that the laws of physics were slightly different, gravity stronger, electromagnetism weaker, nuclear forces out of balance. Life would never have arisen in those worlds. And because of that, no observers would exist to sit around and ask, why is the universe this way? So of course, Carter argued, we shouldn't be shocked to discover that the version of the universe we happen to live in is one that permits life. In his words, what we can expect to observe must be restricted by the conditions necessary for our presence as observed. This idea is known as the weak anthropic principle. It doesn't say the universe was designed for us. It simply points out that we couldn't possibly find ourselves in a universe where life was impossible. To use an analogy, it's like a fish wondering why water exists. The fish never sees the countless places where water isn't, because without water there wouldn't be any fish to do the wondering. But there's a stronger version too, and this is where the idea gets more controversial. The strong anthropic principle suggests that the universe must have the kind of properties that allow life and observers to emerge. It implies that there is something fundamental about the laws of nature that makes life not just possible, but inevitable. Some have even gone further, hinting that the universe is in a sense compelled to produce beings capable of looking back at it. That borders on philosophy or even theology, and many scientists are cautious about venturing into that territory. Still, the anthropic principle has been surprisingly useful. Steven Weinberg, who won the Nobel Prize in Physics, famously applied it in the late 1980s to estimate the value of the cosmological constant, the number that controls how fast the universe expands. If the constant were much larger, galaxies would never form. If it were much smaller, the universe might collapse back on itself. Weinberg reasoned that given our existence, the cosmological constant must fall within the very narrow window that permits observers. His estimate came astonishingly close to what was later confirmed when astronomers discovered dark energy. For a principle that some dismiss as philosophy, it gave a genuine, testable prediction. Even Stephen Hawking, while skeptical of how far the principle could be stretched, admitted it had value. In A Brief History of Time, he wrote that the anthropic principle can help us understand why certain constants take the values they do, even if we never find a deeper theory to explain them. He wasn't suggesting the universe was built with intent, but he recognized the logic. Only a universe with the right numbers could ever be observed. Of course, not everyone buys into this. Richard Feynman once mocked fine-tuning arguments as misleading, saying they make the universe sound too perfect. He warned that they risk confusing cause and effect, because just noticing that life exists doesn't mean the universe was arranged for it. Others have argued that the anthropic principle risks being a scientific dead end. If we say the universe is this way because otherwise we wouldn't be here, we aren't really explaining anything. It can feel like giving up on finding a deeper answer, but the very fact that it divides opinion is what makes it so important. The anthropic principle sits at the border between science and philosophy. It doesn't give equations or experiments, but it forces us to face the possibility that our perspective as living beings biases how we interpret reality. Maybe the universe looks fine-tuned because we are only sampling one version of reality, the version where life works. In countless other possible versions, nothing exists to notice. There's also a subtle danger hidden in the principle. When we say the universe seems perfect for us, we risk forgetting that us means humans on Earth. What if life could take radically different forms in universes we might think of as hostile? A world with different constants might not host carbon-based creatures, but could it give rise to other structures capable of self-organization, memory, or awareness? The anthropic principle, as usually phrased, assumes we know what life must look like. In reality, we don't. Still, it remains one of the only frameworks that grapples with the shocking improbability of our universe. Either the constants of physics are just right because of sheer luck, or they are the product of deeper necessity, or there are countless other universes out there with different numbers, and we just happen to live in this one. Whichever of those turns out to be true, the anthropic principle is the doorway into that conversation. That's why some scientists grudgingly accept it, even if they dislike its vagueness. It may not give a final explanation, but it points us toward the real puzzle, the fact that reality itself has conditions that seem improbably precise for life, and whether you see that as chance, necessity, or something more profound, you can't escape the fact that without this improbable balance, we wouldn't be here asking the question at all. Chance, necessity, or design. Once we accept that the universe looks remarkably fine-tuned, the next question is unavoidable. Why? Are the laws of physics set the way they are because of pure chance? because they had no choice but to be this way, or because some deeper design put them into place. Each of these possibilities has been argued for centuries, from philosophers in ancient Greece to modern cosmologists, working with particle accelerators, and none of them give an easy answer. The first explanation is chance. Maybe the universe just happened to roll the dice and land on a combination of numbers that made life possible. At first glance, this feels absurd. After all, the odds of constants like gravity, electromagnetism, or the cosmological constant falling into such a narrow, life-friendly range are so tiny, they're almost impossible to imagine. Yet, many scientists remind us that improbable events still happen. Roger Penrose once calculated that the odds of our universe starting in a low-entropy, life-permitting state were astronomically small, something like 1 chance in 10 to the power of 10 to the power of 20. Numbers that large stop having intuitive meaning, but his point was clear. It seems beyond unlikely, and yet we're here. To say it's chance might feel like hand-waving, but it is still logically possible. The universe doesn't owe us probability that feels comfortable to human minds. The second option is necessity. Maybe the universe could never have been different. Einstein himself leaned in this direction when he said he wanted to know whether God had any choice in the creation of the world. By God, he didn't mean a deity in the traditional sense, but rather whether the structure of physics was forced. Was there only one possible set of laws, one possible arrangement of constants that could be self-consistent? If so, life wouldn't be a miracle of chance, but an inevitable outcome of the mathematics that underlies reality. This idea motivates the search for a so-called theory of everything. If physicists can unify quantum mechanics and general relativity into one framework, maybe they'll discover that the values of all the constants we see, Planck's constant, the mass of the electron, the strength of the forces, were not free to vary, they were locked in from the very beginning. The third explanation is design. This is the most controversial because it suggests intention behind the universe's structure. Historically, thinkers like Isaac Newton often saw divine craftsmanship in the orderly laws of nature. Even in modern times, some scientists and philosophers argue that the fine-tuning is too precise to be coincidence. The physicist Paul Davies has written that the impression of design is overwhelming, even if we stop short of assigning that design to a conscious creator. Theologians see it as evidence of purpose, while others interpret design more loosely, as if the universe is shaped by principles we don't yet understand. Of course, these three explanations aren't mutually exclusive in how they're debated. The multiverse idea, for instance, tries to combine chance and necessity. If there are countless universes, each with different laws, then it's no surprise that at least one would have the right conditions. We happen to live in that one. That still feels like chance on the local level, but necessity on the cosmic scale. Given enough universes, life was bound to show up somewhere. Critics like George Ellis point out that this slides close to unfalsifiable speculation, but it shows how deeply the puzzle of fine-tuning pushes people toward radical ideas. The perennial argument over whether the universe arose by sheer chance, rigid necessity, or intentional design has shifted with every new scientific era. In the 18th century, when natural theology was popular, design dominated. In the 20th century, as physics revealed the strangeness of quantum mechanics and relativity, necessity seemed plausible. Laws too elegant and interlocked to be random. Today, with multiverse theories on the table, chance is back in the conversation, although many physicists find it unsatisfying, because it doesn't explain why anything exists at all. What's striking is that the debate hasn't really ended, it has only grown more sophisticated. Scientists like Sean Carroll caution that we should be careful not to force cosmic questions into a human framework of probability or intent. He argues that maybe the universe simply is, and our drive to label it as chance, necessity, or design says more about our psychology than about physics. Yet even he admits the fine-tuning puzzle is one of the most profound in all of science. So where does this leave us? With three broad doors, each unsatisfying in its own way, chance feels improbable, necessity feels unproven, and design raises questions that step outside of science altogether. And yet, the universe demands an answer. Every atom of our bodies, Every star in the sky, every galaxy drifting through space is bound up in this puzzle. Whether by accident, inevitability, or intention, reality ended up in a form that allows us to exist, and we still don't know why. The multiverse hypothesis. If there's one idea that has shaken the fine-tuning debate more than any other, it's the multiverse. On the surface, it sounds like science fiction, countless other universes, each with its own laws of physics, branching out like bubbles in an infinite cosmic foam. But for many physicists, the multiverse isn't just a fantasy. It's a serious attempt to answer why our universe looks so improbably suited for life. To understand why scientists began taking this idea seriously, you have to go back to the Big Bang and the strange physics of cosmic inflation. In the 1980s, the physicist Alan Guth proposed that in the earliest fraction of a second after the Big Bang, space itself expanded at an unbelievable rate, far faster than the speed of light. This inflationary model explained a lot of puzzles: the uniformity of the cosmic microwave background, the distribution of galaxies. But it came with an odd consequence. Once inflation starts, it doesn't necessarily stop everywhere at once. Some regions slow down and form universes like ours, while other regions keep expanding, endlessly spawning new pocket universes. In this view, our universe might be just one bubble in a never-ending froth. That's where the fine-tuning puzzle meets the multiverse. If there are countless universes, each with slightly different physical constants, then the fact that we live in one with the right numbers isn't surprising at all. It's like buying every lottery ticket. Improbable results are guaranteed somewhere, and we just happen to live in the winning draw. This idea turns fine-tuning from a mystery into a kind of statistical inevitability. Brandon Carter's anthropic principle, which once felt like a philosophical trick, suddenly has a physical backdrop. It's not that the universe was made for us, it's that we happen to exist in one where existence is possible. But as elegant as it sounds, the multiverse is controversial. The theory is often branded as unfalsifiable, offering no testable predictions to confirm or refute it, which leaves many scientists questioning whether it veers into the realm of philosophy rather than rigorous science. In other words, the most obvious problem here is evidence. We can't step outside our own universe to see the others. Andre Linde, one of the key figures in developing inflationary theory, admits the multiverse is hard to test directly. It exists at the edge of what physics can describe. Cosmologist George Ellis has likewise cautioned that without the possibility of empirical testing, such ideas risk moving beyond the scope of science itself. And yet, hints do keep surfacing. Some cosmologists have suggested that subtle anomalies in the cosmic microwave background radiation, the faint afterglow of the Big Bang, could be scars from collisions with other universes. Nothing definitive has been found, but the fact that researchers are even looking shows how seriously the idea is being taken. In particle physics too, the multiverse pops up unexpectedly. Theories like string theory, which attempt to unify all the forces of nature, predict not one unique universe but a vast landscape of possible ones. Something like 10 to the power of 500 different combinations of physical laws. If that's true, then our universe is just one realization among a practically infinite library. What makes the multiverse so gripping isn't just the science, but the way it reframes the entire debate. Instead of asking why our universe is fine-tuned, it asks why assume it's the only one. If countless universes exist, then our sense of specialness fades. We're not at the center of a cosmic miracle. We're a natural outcome of a vast ensemble, most of which are lifeless. To some, this is comforting. It removes the need for improbable luck or divine design. To others, it's unsettling because it makes our universe feel small, even disposable. There's also a deeper philosophical question here. If there are infinitely many universes, each with different laws, then anything that can happen does happen somewhere. There would be universes with no stars, universes that collapse instantly, universes with bizarre laws beyond our imagination, and somewhere universes almost identical to ours, with Earth, with people, maybe even with someone listening to these words again in a slightly different way. The thought is dizzying, and it blurs the line between science and metaphysics. Sean Carroll, a theoretical physicist, argues that while the multiverse is hard to test, it's not unscientific. He compares it to the idea of atoms in the 19th century. Atoms were once invisible and undetectable, yet the evidence for them built up until they became the foundation of physics. The same could be true for the multiverse. We may never see another universe directly, but if our best theories predict it, and if those theories are confirmed in other ways, then rejecting the multiverse would be ignoring where the evidence points. Critics counter that this is a dangerous move. If every possible set of laws exists somewhere, then fine-tuning becomes meaningless. You can't explain why the constants are what they are. You can only shrug and say, in some universes they're like this, in others they're not. To people like Lee Smolin, this is unsatisfying. He's proposed an alternative, cosmic natural selection. In his view, universes reproduce through black holes, with each new universe perhaps tweaking its constants slightly. Over countless generations, universes that make more black holes outcompete those that don't. By coincidence, the same conditions that maximize black hole production also happen to allow life. It's speculative, but it has the advantage of offering a mechanism that can, in principle, be tested. Even with all these debates, the multiverse remains one of the boldest attempts to answer the question of why the universe is so tuned for us. It shifts the burden from asking why these numbers to asking why this universe, and in doing so, it forces us to consider that the cosmos might be far stranger and far bigger than we ever imagined. For many people hearing this for the first time, the thought lingers. It's not just the science, it's the scale of it. If there are countless universes, then our entire story, every triumph and tragedy, plays out in one tiny corner of an infinite reality. That perspective can make us feel insignificant, or it can make us feel part of something unimaginably vast. Either way, it's hard to hear about the multiverse and not want to hear it again, because it stretches the imagination beyond its usual limits and forces us to see existence in a completely new light. Cosmic evolution and self-organization. When people talk about fine-tuning, it often sounds as though life sits on a razor's edge, barely clinging to possibility. But there is another way to tell the story, one where life is not a rare fluke, but the expected outcome of the universe's long history. This perspective sees the cosmos as a system that builds complexity layer by layer, with each stage setting the stage for the next. Instead of needing everything to be delicately prearranged, order emerges naturally through the steady logic of physics and chemistry. We can start this story at the earliest possible moment. Right after the Big Bang, the universe was not the dramatic fireworks display people often imagine. It was hot, dense, and surprisingly uniform. Yet, thanks to tiny fluctuations, minute differences in density, measured today in the cosmic microwave background, gravity had something to work with. Over time, those small ripples grew. Regions with slightly more matter pulled in more, snowballing into vast structures. Galaxies formed not because someone fine-tuned them into existence, but because the laws of physics make clumping inevitable when matter is unevenly spread. This is the first glimpse of self-organization at the largest scale, complexity rising naturally out of simplicity. From there, stars began their role as cosmic engines. Fusion inside their cores turned the most basic elements, hydrogen and helium, into carbon, oxygen, nitrogen, and iron. This is basically the ingredient of life. When massive stars died, they exploded in supernova, scattering those elements into space. Every rock, every ocean, every living cell is built from this recycled stardust. It's not merely that we are alive in the universe. The deeper truth is that the universe is alive within us. Carl Sagan captured it simply when he said, "We are made of star stuff." And in truth, this was not the result of fragile precision, but of a universal process. Whenever stars live and die, they enrich their surroundings with the building blocks of complexity. The next leap forward came on planets. On Earth, energy from the sun, the chemistry of water, and the restless movement of molecules created an environment full of possibility. Here we must remind ourselves that molecules are not passive. They react, bond, and rearrange in endless combinations. When placed in the right conditions, liquid water, stable temperatures, a steady energy source, chemistry naturally explores countless possibilities. Some of those possibilities reinforce themselves, repeating patterns again and again. This is the essence of self-organization. We see it in simple familiar systems. Snowflakes form elaborate symmetric patterns without anyone arranging them. Chemical oscillations like the Belousov-Zhabotinsky reaction create striking rhythms of color and concentration without outside guidance. Even hurricanes organize chaotic air into stable spirals that persist as long as they are fed by warm water. These are not miracles. They are physics and chemistry showing a tendency toward order when energy flows through a system.
Nobel laureate Ilya Prigogine called such systems dissipative structures because they maintain themselves by taking in and releasing energy. Life, in this sense, can be seen as the most advanced, dissipative structure the universe has produced. The leap from chemistry to biology is still mysterious, but experiments have shown it may not be as unlikely as it sounds.
In the 1950s, Stanley Miller and Harold Urey ran an experiment that simulated early Earth conditions: water, methane, ammonia, hydrogen, and sparks to mimic lightning. After a week, they found amino acids, the basic components of proteins. This was a landmark moment. It showed that the ingredients of life could form spontaneously under natural conditions. Later studies have gone even further, producing nucleotides, simple cell membranes, and metabolic cycles under laboratory conditions. None of this proves we know exactly how life began, but it demonstrates that chemistry leans toward complexity when given enough time and the right environment. Once the first molecules learned to replicate, Darwin's principle of natural selection took over. Small differences meant some versions copied themselves better than others, and those survivors passed on their advantages. Over billions of years, this simple mechanism drove the rise of cells, multicellular organisms, ecosystems, and eventually brains capable of reflecting on the process itself. Life became more complex, not because the universe was delicately balanced on purpose, but because selection favors complexity when it improves survival and reproduction. Biologist Stuart Kauffman described this as order for free. In his models, networks of interacting molecules naturally fall into stable patterns. Instead of chaos, you get cycles, feedback loops, and balance. Complexity is not fragile. It is the natural result of interactions multiplying across time. Seen in this way, life might not be a rare accident at all. It could be a universal phenomenon, the likely outcome wherever physics and chemistry are given enough room to work. Evidence for this possibility is growing beyond Earth. On Titan, Saturn's largest moon, lakes of methane and ethane sit under a thick atmosphere rich in organic chemistry. On Europa and Enceladus, liquid oceans swirl beneath ice, kept warm not by sunlight but by tidal heating from their parent planets. Mars once had rivers, lakes, and perhaps even seas. In each of these worlds, the ingredients of complexity are stirring. They may not mirror Earth perfectly, but they remind us that chemistry is restless across the cosmos. If self-organization is universal, then life might not be confined to this planet. This shifts the way we think about fine-tuning. Yes, the constants of physics must fall within certain ranges, but once they do, the drive toward complexity may take care of the rest. The universe doesn't just allow life, it produces pathways toward it. From ripples in the early universe to stars and elements to chemistry and biology, each stage naturally follows from the last. What looks like a chain of improbabilities can also be seen as the expected arc of cosmic evolution, and this is the perspective that makes people stop and think again after hearing it. Life isn't perched on the edge of impossibility. It is the expression of the universe's long habit of turning chaos into order. Stars, storms, molecules, and minds are all part of the same pattern. We don't sit outside the universe wondering why it's tuned for us. We are what happens when the universe runs patiently for billions of years. Whenever we talk about the universe being perfect for us, there's a danger hidden in the way we frame the question. We only know one kind of life, our own. We only know one kind of world, Earth. And we only have one set of tools to study reality. Human minds shaped by evolution on this specific planet. That means when we look at the cosmos, we are not neutral observers, we are biased, and those biases shape the way we interpret fine-tuning. The anthropic principle hinted at this earlier. Of course, we find ourselves in a universe where life can exist, because if it couldn't, we wouldn't be here to notice. But it goes deeper than that. We tend to assume that the universe had to look this way for life to be possible. What if that assumption is wrong? What if life could take forms that don't resemble us at all? For example, we think of water as essential on Earth. It acts as the solvent of life, carrying nutrients, enabling chemical reactions, and shaping ecosystems. But does life anywhere else need to use water? Some astrobiologists speculate about ammonia-based life, methane-based life, or even forms of life that don't rely on liquids at all, but instead on plasma or exotic chemistry we can't yet imagine. On Titan, with its methane lakes and organic haze, researchers like Chris McKay at NASA have suggested that a completely alien kind of metabolism could, in principle, operate. To us, Titan looks hostile, but to something adapted to its chemistry, Titan could feel as natural as Earth feels to us. This highlights the bias in how we judge habitability. We call Earth's conditions perfect, but they're only perfect for the kind of life that evolved here. Shift the lens, and a different set of conditions could seem equally perfect to another observer. A being made of plasma in a star's atmosphere might consider Earth hopelessly cold and dull. A methane-based creature might find our oceans toxic. Our perspective is narrow, but it's the only one we have, so we mistake it for universal truth. There's another layer to this bias. The way our brains interpret probability, humans are bad at understanding very large numbers. When scientists talk about the odds of fine-tuning being 1 in trillions, it sounds impossible, but the universe is not rolling dice in a way we can easily grasp. What feels improbable to us may not be improbable at all. On cosmic scales, as Sean Carroll has pointed out, sometimes what looks like fine-tuning is simply the result of us expecting the universe to align with our intuition, when in reality it doesn't have to. Even the phrase fine-tuned can mislead us. It makes it sound as though there is a tuner, a hand adjusting the knobs of reality to get the settings just right, but that's a metaphor born from human experience. We tune instruments, we adjust machines, so we imagine the cosmos being tuned in the same way. The truth may be stranger, the constants might just be what they are, without any deeper reason we can comprehend. Our search for purpose might be us projecting human categories onto a reality that doesn't share them. This doesn't mean the fine-tuning puzzle isn't real. It is, but it reminds us that the puzzle may be partly a trick of perspective. We look out at the universe and see it as perfectly suited to us. But perhaps the more accurate way to say it is that we are perfectly suited to it. Life evolved under these conditions and could not have evolved under others. From this angle, it is less about the universe aligning with us, and more about us being shaped to fit the universe we found ourselves in. In a sense, life could be an adaptation to the cosmos, not the other way around. What feels like perfection might simply be the product of billions of years of trial and error, with only the successful combinations surviving to look back and marvel at how well it all worked out. This doesn't cheapen the mystery, it deepens it, because if our perspective is limited, then we can't be sure how wide the possibilities really are. We don't know what other forms of life are possible. We don't know if consciousness is rare or common. We don't know if our sense of improbability is justified, or if it's simply a reflection of our human inability to grasp scales of chance. And until we explore beyond Earth, we are judging the entire universe based on a single example, ourselves. That is both humbling and thrilling. Humbling because it shows how narrow our window is. Thrilling because it means we may have only scratched the surface of what life, habitability, and fine-tuning really mean. The perfection we see may not be the universe's perfection at all. It may just be the story we tell from our limited vantage point. For most of human history, the stars were silent. We could look at them, chart their movements, and build myths, but we had no way of knowing whether any of them had worlds of their own. That changed in the late 20th century. In 1995, astronomers Michael Mayer and Didier Queloz announced the first confirmed discovery of an exoplanet orbiting a Sun-like star, 51 Pegasi Ba. It was a breakthrough that opened the floodgates. Since then, thousands of exoplanets have been found, and the count grows every year. The Kepler and TESS missions have revealed that planets are not rare exceptions. They are the rule. Nearly every star we see in the night sky likely has planets of its own. Among them are worlds roughly the size of Earth, orbiting in the so-called habitable zones of their stars, where temperatures could allow liquid water. This discovery has transformed the fine-tuning conversation from an abstract philosophical question into an empirical search. Instead of asking whether the universe is capable of supporting life, we are now asking where it already might be doing so. Each new world discovered adds data to that question. But even more exciting are the next generation telescopes designed not just to find planets, but to study their atmospheres. The James Webb Space Telescope, with its infrared sensitivity, is already beginning to analyze the chemical makeup of distant worlds. In the coming years, we may detect gases like oxygen, methane, or other organic compounds in alien atmospheres, the telltale fingerprints of life. It's no longer just speculation, it's a measurable possibility. And with that comes the potential to redefine what we mean by habitability. Some exoplanets orbit red dwarf stars, smaller and cooler than the Sun. Their habitable zones are close in, which means those planets could be tidally locked. One side in permanent day, the other in eternal night. For a long time, scientists assumed that would make them unlivable. But climate models now suggest that with the right atmosphere, heat could circulate and create regions of stability, perhaps even oceans beneath thin clouds. Even moons around giant planets could be habitable if they have internal heating or thick atmospheres. The diversity of potential environments for life keeps expanding, and with it, our understanding of what fine-tuned really means. The more we discover, the more we realize that the universe might not have been designed to produce one kind of life, ours, but many kinds, under many different conditions. Future missions like LUVAIR, HABEX, and the Extremely Large Telescope will push this search further, scanning nearby stars for the faint blue dots that might resemble our own planet. They will look for chemical imbalances that suggest biological activity. A whiff of methane paired with oxygen, for example, would be hard to explain without some kind of living process. But even if we never find another inhabited world, the search itself is reshaping our understanding of cosmic fine-tuning, because every new discovery shows us that life is not isolated in a single configuration of conditions. It is a pattern that may repeat wherever the universe allows. And if that's true, then the universe may not be fine-tuned for life at all. Life may be what the universe naturally does when given time and complexity. Even with all our progress, the fine-tuning question refuses to go away. Every explanation, chance, necessity, multiverse, self-organization pushes the mystery one step back, but never fully removes it. If the multiverse exists, why does it exist at all? If the laws of physics naturally generate complexity, why do those laws exist in the first place? Science is superb at describing how things happen, but when it comes to the ultimate why, it often meets a wall. Physicist Paul Davies once said that the laws of physics seem to have been set up in a way that allows the universe to be self-aware. It's a poetic statement, but also a haunting one, because it suggests that the deepest question of all might not be about numbers or equations, but about consciousness. Why should a universe born in a burst of energy and expanding into silence eventually give rise to beings who can think, feel, and ask where it all came from? Some scientists argue that consciousness itself might be a fundamental feature of the cosmos, not a latecomer. Others hold that it's an emergent property, the inevitable outcome of matter becoming complex enough to reflect on itself. Either way, the existence of minds capable of wondering about the universe adds a strange twist to the story of fine-tuning. The observer and the observed are not separate. We are part of the very system we're trying to understand. The more we learn, the more the universe seems to blur the line between physics and philosophy. Perhaps, as physicist Freeman Dyson once said, the universe knew we were coming, or perhaps it didn't. Maybe existence requires no reason at all, only the relentless unfolding of possibility. And yet, for all the equations, models, and telescopes, there's a feeling that science alone might never be able to close this question, because fine-tuning isn't just about physics, it's about meaning. It's about why there is something rather than nothing, why the void sparked light, why matter organized itself into stars, planets, and life, why, out of infinite chaos, something as unlikely as understanding could emerge. In the end, maybe that's what makes the fine-tuning puzzle so powerful. It reminds us that even in an age of supercomputers and particle colliders, the greatest mystery is not what the universe is made of, but why it exists in the first place, and why we are here to notice.